Section 2.5 is going to be about all the different transformations of functions. Okay, so the first thing we're going to go into the transformations is we're going to look at the different types of functions that there are, so you can remember all the different families that we talked about in the previous lectures. These are the different types of common functions that we talked about, such as f of x equals to c, f of x equals x, f of x equals absolute value of x, f of x equals x squared, f of x equals the square root of x, and f of x equals x cubed, f of x equals the cube root of x. So these are the different families of functions. Now, there were a lot of attributes that we cover from section 2.2 and 2.1, such as the following: domain, range, if it's even or neither, and if it's increasing, decreasing, or constant. So we cover those kinds of things. Now, the function f of x equals c. C, it's just a number. That is represented by a constant function, which is just a number. Now, the graph of that is going to be a horizontal line. That's what we cover. The domain of a horizontal line is from negative infinity to positive infinity, because it contains any value of x on the negative side and on the positive side. So negative 5, negative 6, all the values of x can be found on this graph, from left all the way to the right. Now, the range of this function contains only one single value, and that value of c, wherever it crosses the y-axis, because that's the only y value on that horizontal line. Now, the function is always constant from negative infinity to infinity, because it's always horizontal. And the function is even because it reflects to itself over the y-axis. If I reflect it over the y-axis, it's going to give itself. It's going to create itself on the other side. It's going to reflect to the same graph. So, then the next one we cover is f of x equals x. This one is going to look like a straight, just a regular slanted or sloped line. Now, for this one, we know that the domain of this one is going to be from negative infinity to positive infinity, because it keeps on going both to the left and it keeps on going to the right, which means every value of x, positive or negative, is going to be on the graph. The range is the same thing, is negative infinity to positive infinity, because every value of y, negative or positive, is on the graph. All the negative values can be found on the graph. All the positive y values can be found on the graph. The function is always increasing, f of x equals x, because it keeps on going from left to right. It keeps on going up from left to right. And we said that the function is odd because it reflects creates a reflection over the origin. Now remember that origin symmetry means the following: that if I reflect it over the y-axis and then over the x-axis, it's going to create itself. So for example, if I reflect this piece of the line over the y-axis, it is going to create this, but then if I reflect it over the x-axis, it's going to create its own. So that's a double symmetry. Okay? So that's what it means by an odd function. Next one. The next function that we have is f of x equals the absolute value of x. That one is going to have the shape of a V. We talked about that one too. Now, the domain of this function is negative infinity to positive infinity, because this graph keeps on going both to the left and to the right, meaning that any negative value of x can be found on the graph, and any positive value of x can be found on the graph. So it's from negative infinity to infinity. However, the range is not the same thing, because the lowest value of the absolute value of x, the lowest value of y, it is going to be 0. This is the lowest. This is my y. And from there, it keeps going up. So if it goes up, keeps going up, that means it's going to go all the way up to positive infinity. So that's my range, from 0 to infinity. Now, the function, it is both increasing and decreasing, because you see that on the first half right here, the graph is coming down from left to right, meaning that it is decreasing from the beginning, which is from negative infinity, until it gets to 0 right here. That's where it stops decreasing. But then it is increasing anywhere after 0. So from 0 to positive infinity, it is increasing. And then we said that the function is even, because if I reflect it over the y-axis, it's going to create its own the same graph. So if I reflect it over the y-axis right here, it creates itself. So So that's the definition of even. Now, the next function we cover is f of x equals x squared. That one creates the shape of a parabola, or a U-shape. Now, the domain of the function of any U-shape, it's going to be also the same, from negative infinity to positive infinity, because it keeps on going both to the left and it keeps on going to the right. So it contains all of the x values of x in its graph, negative values of x and positive values of x. Now, the range of this function, the lowest value of y right here is going to be 0. And this graph keeps going all the way up, so it never stops. So it's going to go all the way to infinity. So it includes 0 and it goes to infinity. Now, the function is both decreasing and increasing. As you can see, it is first decreasing on the first half because it's coming down from left to right. So from negative infinity all the way until it gets to 0, it is decreasing. And anywhere from 0 to positive infinity, it is increasing. And then the function is even because if I reflect it over the y-axis, it's going to create its own graph. So if I reflect this piece over the y, it creates its own. Okay. Now, the next one is f of x equals the square root of x. Now, I want you to remember this for the next section after this one, for section 2.6. It's going to be a very important case. Now, f of x equals the square root of x looks like an eyebrow shape. So that's basically what we see. Now, on this one, the domain is not negative infinity to positive infinity. Keep that in mind. So what do we see the domain is on this one? It is 0 to infinity, because it starts from 0 right here, and then it keeps going to the right, all the way to infinity. It just keeps going and going and going, right? So that's where all the values of x are in the graph. Now, for the range, the lowest value of y, it is down here. So it starts from 0, and this graph keeps going up, keeps going up, keeps going up, so it's going to go to infinity also. So from 0 to infinity. So the function is increasing only, okay? But it is increasing from here to infinity, and it is only increasing, right? From 0 to infinity. And the function is not even or is not odd, because for even, remember that the function is required to reflect over the y-axis. But if I reflect it over the y-axis, we should be able to see a piece of the graph on this side, but there's nothing on the left side. So there is no y-axis reflection. Now, for odd, I need to see this. First of all, well, it's going to reflect over the y-axis right here, but this is not going to be the graph. Then it's going to reflect over the x-axis. So what I should see should be down here. But there's no graph on this side either. Okay? So there is no y-axis symmetry or origin symmetry. So this one is not even or not odd. Okay? So this is the only function from the family that we cover for which the domain is not negative infinity to positive infinity. And this is one of the attributes that we're going to talk about in the next section afterwards. Section 2.6. Now, the last function that we're going to look at is f of, well, there's two more. F of x equals x cubed. Now, that one is called the cubic function, and we can see that one has the shape of like an S or a snake shape. And this one, we can see that it keeps on going to the right side, and it also keeps on going to the left side all the way, meaning that all of the negative values of x and all of the positive values of x will be on the graph of this function. So the domain is negative infinity to positive infinity. Now, the range of this function keeps on going down and it keeps on going up, meaning that all the negative values of y will be on the graph and all the positive values of y will be on the graph. So the range is also negative infinity to positive infinity. Now, the function is always increasing, as we can see. So it is constantly going up from left to right, which means that it is always increasing. And we can also say that the function is odd because I can reflect it over the y and over the x to create its own graph. Let me give you an example here. So let's say, for example, if I reflect this graph onto the y-axis right here, what is it going to look like? It is going to look like this. So if I create a reflection of this onto the y-axis. But that's not all. Then what happens if I reflect it over the x-axis? It is going to create its own graph. It doesn't create something new. It creates something that was already there. So when I do a double reflection over the y-axis and then over the x-axis, it creates its own graph, meaning that it is an odd function because it has what we call origin symmetry. And last but not least is f of x equals to x cubed. I mean not x cubed, but the cube root of x. That one looks also like a snake shape, but that one goes more than to the sides. Okay. So on this one, we can see that the graph keeps going to the right and the graph keeps on going to the left. What does that mean? That every value of x is going to have a point on this graph. So either whether it's a negative value of x or a positive value of x, all of them will be on the graph. So the domain is negative infinity to positive infinity. Now, for the wrench, we can see that if the graph keeps on going all the way down and the graph keeps on going all the way up. So that means that all the negative values of y are on the graph and all the positive values of y will also be on the graph. So that's why the range is also negative infinity to positive infinity. The next one is the function is always increasing, as we can see, increasing because it keeps on going up from left to right. Anywhere from negative infinity to positive infinity, it is always going up. And then the function is an odd function because it is a double reflection. So if I do a double reflection to this function, look what's going to happen. So if I reflect this piece of the graph onto the y-axis, it is going to create this. And if I reflect it onto the x-axis, it is going to create its own graph. So it doesn't create anything new. So that's why it is an odd function, because it has what we call origin symmetry. Origin symmetry means that it reflects onto the y-axis followed by an x-axis reflection, and it doesn't create anything new. It creates its own graph. Now, we're going to start with the transformations. Now, the first transformation that we're going to discuss is called vertical shifts. We kind of discussed this one a little bit in section 2.1. Whenever you have a function, f of x, and another function that looks similar to it, the only difference between them is that that other function has a plus c, plus a number. That plus a number is going to basically make the function shift up that many units. Likewise, if I have a function that looks the same as another one, the only difference is that the other function has a minus c. That minus c is going to make the function go downward that many units. Okay? And remember what we talked about is that this value of plus c or minus c is going to be either added or subtracted to the y values. It affects the y values. So let's start performing some of the transformations. So we're going to begin with this problem. It says, use transformations of f of x equals the cube root of x to graph the following function. G of x equals cube root of x minus 4. So the first thing we need to do is we need to begin by graphing the function cube root of x, and then we do the transformation. Okay, that should be the start. So let's go ahead and begin with the cube root of x. So we're going to start with the table, just like I showed you in section 2.1. But now keep the following in mind. I cannot utilize the values negative 2, negative 1, 0, 1, and 2 for my table in this case, because for the cube root, in order for us to get an integer value as a solution, we need to use perfect cubes. Perfect cubes, we have 5 that we can use with a negative 10 and positive 10. Negative 2 cubed, for example, negative 2 cubed is going to be negative 8. So that's one of the values that we can use that is a perfect cube. Negative 1 cubed is negative 1. 0 cubed is 0. 1 cubed is 1. And 2 cubed is 8. So these are the 5 values that we can use for the cube root. Because now, if I want to get the cube root of negative 8, remember what that means from the radical section. We're looking for a number that when cubed it gives me negative 8, and that number was negative 2. That's why we have to use perfect cubes. In this one, it means the cube root of negative 1 means that we're looking for a number that when cubed gives me that negative 1, and that is negative 1. On this one is the cube root of 0, so we're looking for a number that when cubed it gives me 0, and that would be 0. Cube root of 1 means that we're looking for a number that when cubed gives me 1, and that is 1. And the last one is cube root of 8. In this one we're looking for a number that when cubed equals to 8, and that number is 2. So I'm gonna put right here on the bottom so you can follow. For the function f of x equals cube root of x, we got the following table. The table is negative 8, comma, negative 2, that is 1 point. Negative 1, comma, negative 1, that's another. 0, comma, 0. Then we got 1, comma, 1. And then we got one last point in here, which is going to be 8, comma, and 2. So let's graph that original function f of x. So negative 8, negative 2, it's going to be located here. Then negative 1, which is here. Then 0, 0, 1, 1, and 8, comma, 2. And just like I showed you right now on the concepts, the cube root looks like an S shape, basically going sideways. This is my cube root of x, I'm sorry. So this is the function f of x. Now, to create the function g of x, there is only one thing we have to do. So we want to transform this function into this function, cube root of x minus 4. Okay. So based on the definition, what does that minus 4 is going to do to the function? Basically, we talked about it. It is going to create one little change, and it is going to basically bring the graph 4 units downward. And according to the definition, remember that that minus 4 is going to be subtracted to the y values. That's what is going to have as an effect. So that's going to give us negative 8, comma, and when I subtract negative 2 minus 4 is negative 6. Negative 1, comma, negative 1 minus 4 is negative 5. 0, comma, 0 minus 4 is negative 4. 1, comma, 1 minus 4 is negative 3. And then 8, comma, 2 minus 4 is negative 2. This is going to be the table for the function g of x. So let's graph it in here. Negative 8, comma, negative 6 is going to be here. Negative 1, comma, negative 5. 0, comma, negative 4. 1, comma, negative 3. And 8, comma, negative 2. And then we connect those points, and this is going to be the graph of g of x. Now, a lot of the questions in this section, they're going to ask you to describe the transformation. So I'm going to be describing the transformation on every problem. There are some that don't ask for that, but I'm going to write it for all. So what we're going to say is the following, that the graphs are basically the same. So we're just going to say that the graph of g of x is the graph, exactly like the definition says, is the graph of f of x, but shifted 4 units down or downward. And this is basically the description of how the graphs are related to each other. The graph of g is the same as this graph, but it is shifted 4 units down from f of x. Now, the next definition we are going to talk about is horizontal shifts. Now, when does a horizontal shift happen? So let's take a look at this. It happens again when we're adding or subtracting a constant, c also, but that constant, as you can see, it is being added or subtracted to the x, meaning it is, you're going to basically see it if it is inside of the square root, if it is inside of the parentheses, if it is inside of the absolute value, and so forth. That's how we're going to find out that it's going to be added or subtracted to the x. Okay, so that's basically what it does. Now, if you have a plus inside, a plus c, that is basically going to make the graph shift to the left c units. It's going to go in the opposite direction of the sign. If the function has a minus c inside, then this graph is going to shift to the right c units. So remember this, if it goes to the left c units, you're just going to subtract that number here from the x values. If it goes to the right c units, in other words, when you have a minus c, you're going to add that number to the x values. Okay, so it's going to be the opposite operation. Let's take a look to this problem right here. It says, use transformations of f of x equals the square root of x to graph the following function. Now we're going to start by creating a table for the function f of x. Now we talked about the square root in section 2.1, and remember that you need to use some special values when creating your table, and that is your perfect square. Of course, remember that the square root cannot contain a negative, so it's going to start from 0, 1, then 4, and then 9. And this is as much as we can fit in. So we're going to start by getting, of course, the square root. So square root of 0 is going to give us 0, square root of 1 is 1, square root of 4 is going to give us a 2, and square root of 9 is going to give us a 3. So these are the values for the function f of x, square root of x. So the table is going to be 0, 0, 1, 1, 4, 2, and 9, 3. So let's create the graph. 0, 0, 1, 1, 4, 2, and 9, 3. Now, for the function g of x, now on this one we have two transformations that must be applied. We have one of them that is plus 1 inside, and then we have the plus 1 on the outside. Now, keep in mind that sometimes what I'm going to tell you next is not going to matter depending on the transformations you have in a specific question. But I'm just going to rather use the same format for all. Now, whenever you have multiple transformations, there is an order that we actually have to follow in the to perform the transformations. And like I said, sometimes depending on which transformations you are given, the order doesn't really matter. But I'm still going to follow that order. Okay? So what do I mean by sometimes the order doesn't really matter? That sometimes if you do it in no matter which order you do it, it's going to give you the same result. But that only works when you have certain transformations, and I want you to discover that. So whenever, for the actual order that you need to follow, you need to keep the following in mind, that a horizontal shift is always first and a vertical shift is always last. So those are the only two things that will actually matter in there. Now, there might be more transformations in specific questions, but the transformation, if we have more than two transformations, just remember that horizontal shift must be first and vertical shift must be last. So we're going to start with the horizontal shift. So the horizontal shift is given by the x plus 1. So what is that plus 1 going to do according to the definition we just covered? Remember, it goes in the opposite direction. That one is going to shift it to the left 1 unit, meaning that you're going to subtract that 1 from the x values. So that's going to give me a negative 1, 0, 0, 1, then 3, 2, and 8, 3. Okay, so that is going to be the first change. So I'm going to graph each transformation. Just keep in mind, when you're graphing your own, you're only supposed to create f of x and the last function, which is h of x. You don't really need to graph this one in the middle, but I'm gonna do it on my demonstrations. So negative 1, 0, it's gonna be here. Then we have 0, 1. Then you have 3, 2. 3, 2. I'm sorry. And the last one is gonna be 8, 3. You can double check it so you can see that it is correct. So for example, what is the x value here? Negative 1, right? What happens if you substitute a negative 1 into the x? Negative 1 plus 1, it's 0, and the square root of 0 gives you this 0 right here. You can check it and you will see that it gives you all those values. So for example, the next one, what is the x value here? 0. So 0 plus 1, it's a 1, and the square root of 1, it's 1. So that's what you see, 0, 1. Now look at the 3. If I put a 3 here, 3 plus 1, it's going to be a 4, and the square root of 4, it's going to give me a 2. So 3, 2, that's what we see. And the last one is also going to give us the same thing. Okay. Now I'm going to create one more graph for this. So let me go ahead and get a graph from the previous question. Okay, let's continue here. So now we're going to create the last graph on this function. Okay. The last transformation that we are supposed to do now is going to be the vertical shift. That one is always my last transformation. So now from here, we're going to go to the square root of x plus 1, but now we're going to do the plus 5 also. And that is going to create my final function, h of x, which is what we need. So, talking about that plus 5, what is that plus 5 going to do to the function? It's going to shift it 5 units up, and that is going to have is going to affect the y value. So it's going to add a 5 to all of the y values on these points. So if I do that, then it's negative 1 comma 5, then 0 comma 6, then 3 comma 7, and 8 comma 8. Those will be the values for h of x. So negative 1, 5, it's going to be located right here, 0, 6, then 3, 7, and then 8, 8. And that is going to be the function h of x that we're looking for. Okay, so the only ones that we need to actually graph would be the original graph f of x and the last one, which is h of x. This one doesn't need to be graphed. It is just my demonstration. Now let's go ahead and describe how the graph of g is related to the graph of f again. So we're going to describe the transformations in the order in which they happened. So we're going to say that the graph of g of x, well, not g of x, but h of x. The graph of h of x is the graph of f of x, but first it was shifted 1 unit to the left, comma, and shifted up or 5 units up or upward. This is basically the description of how the graph of g would be related to the graph of f in this particular question. It was shifted from here to here. It was to move to the left 1, and then it moved up 5 to create this. Now, the next transformation is going to be reflections. Okay. Now, there's two types of reflections that we can have on the graph here. So we have a reflection over the x-axis and reflection over the y-axis. Now, when does each one of them happen? So this is what we're going to talk about. So the reflection over the x-axis happens when you have a negative on the outside of the function. So that negative is going to cause the function to reflect over the x-axis. And what you're going to do is that you're going to multiply all of the y values by a -1. Or you can just say, when I multiply the y values by a -1, it means that you're going to change the signs of the y values. That's what happens when you have an x-axis reflection. And just know that this negative f of x is just the same thing as negative y. That's what the negative f of x basically means. Negative y. Which means multiply the y times a -1. Alright, so now the second reflection you see is a reflection over the y-axis. This one happens when you have a negative, but that negative is on the x specifically. So if you have a negative on the x, that causes the graph to be reflected over the y-axis. And that negative x means that now you're going to multiply all of the x's times a negative, or a -1. So once again, all of the x's will be multiplied times a -1 to create that y-axis reflection. Now let's answer the following questions. Use the graph of f of x to graph the function g of x equals f of -x plus 4. On this one, we don't need to create the graph of f of x. The graph of f of x is already given right here. So all we need to do, we're going to get the points from this function already given. So there are 5 points that we can use for this. So I'm going to say right here, the function f of x contains the points -4, 0, -2, 4, 0, 0, 2, -4, and 4, 0. Now, according to the order of the transformations, remember that 2 things that you need to keep in mind only. The horizontal shift is always first, and vertical shift is always the last thing. Now right here, this function does not have a horizontal shift. All it has is a vertical shift. So my last transformation that I am going to do, it would be the +4. This will be the last one. Okay? So first I need to do the f of -x. That is the first change that I have to apply here. So according to the definition, what is that negative on the x going to cause the function to do? It is going to reflect the function over the y-axis. And the reflection over the y-axis happens because that -x means that all of the x values right here will be multiplied times a -1. So once again, all of the x values will be multiplied times a negative. When I say a negative, it means -1. So if I multiply those x values by a -1, they're going to change the signs. +4, +2, 0, -2, and -4. The y values are going to stay the same. 0, 4, 0, -4, and 0. So I'm going to grab the first transformation. So 4, 0, it's going to be here. 2, 4 is going to be up here. Then 0, 0, then -2, -4, and then -4, 0. And if you connect these points on this graph, you will see that the graph from the original graph, it was flipped over the y-axis. It was flipped this way. So this little piece went to the right side and this piece went to the left side. So it was reflected over the y-axis. Next and last transformation that we need to apply. Now we have a +4. That +4 is going to make it go up 4 units, and that is going to be added to the y values as usual. So that's going to create the points 4, and then 0 + 4, which is going to be a 4. 2, 4 + 4, which is going to be an 8. Then 0, 0 + 4 is a 4. Then -2, -4 + 4 is a 0. And then -4, 0 + 4, it's going to be a 4. And this is going to be your function g of x. Because g of x, this is what it consists of, right? That's g of x. So we're going to graph it. So it's 4, 4, then 2, 8, then 0, 4, negative 2, 0, and negative 4, 4. And this completes my function g of x. Let's go ahead and describe the transformations here and see, how the graph of g is related to the graph of f again. So I'm going to say exactly in the order in which the transformations happen. I'm going to say that the graph of g of x is the graph of f of x, but first of all, it was reflected over the y-axis, and then it was shifted 4 units up or upward. And these are the transformations in the order in which they actually happened. Now, if I would have done this specific example, the other way around, would the answer have been different? It wouldn't, because one of the transformations only affects the x values, the other transformation only affects the y values. Now, whenever there's a transformation, two transformations that affect the same value, either the x's or the y's, then that's when we need to be careful on following the correct order when applying the transformations. If you don't have a transformation that applies to both the x's or the y's, to the x's twice or the y's twice, then you don't need to worry about it in the in the order in which you're doing them on the points. But it really matters when you have those transformations that will affect the same variable. Now, let's take a look to the next problem here. We're going to do this one. So, use transformations of the graph of f of x equals x cubed to determine the graph of the given function h of x equals negative x plus 1 to the third power. So the first thing we're going to start doing here is we're going to create the table for the function f of x. This function is going to be given by the x cubed. So for the table, we're going to use again negative 2, negative 1, 0, positive 1, and positive 2. Now, if I cube these values, negative 2 cubed is negative 8. Negative 1 cubed is negative 1. 0 cubed is going to give us a 0. 1 cubed, it's going to be 1. And 2 cubed, it's going to be 8. So the function f of x equals x cubed gives us the points negative 2 comma negative 8, negative 1 comma negative 1, 0 comma 0, then 1 comma 1, and 2 comma and 8. So let's graph that. Negative 2, negative 8 is right here. Negative 1, negative 1, 0, 0, 1, 1, and 2 comma 8. So x cubed has the shape of an S shape, or we call it the snake shape. So that gives us a graph of f of x. Now we're going to apply the transformations in the order in which they must be done. Okay. So the first thing that needs to be done, remember that the plus 1, that creates a horizontal shift, and according to the definition, horizontal shift must always be the first transformation applied. So we're going to start with that. So the first thing I'm going to apply to this is going to be the x plus 1. And what that plus 1 is going to do to the function there is going to shift it to the left 1 unit, and that is going to be subtracting the x values by 1. So we're going to subtract 1 from the x values. That's the effect that it's going to have on the graph. So then it's going to give me a -3, -8. Then the next one is -1 minus 1, which is -2, -1. Then -1, 0. Then 0, 1. And then is 1, 8. So these are the points for this second transformation. So we have -3, -8. It's going to be down here. -2, -1. Then -1, 0. Then 0, 1. And 1, 8. And this is my first transformation. Oops. So far the graph of f of x was shifted to the left 1 unit to create this. That's all the change that we had so far. Shifted to the left 1 unit. Second and last transformation, you see we have a negative. That's going to be my last transformation that I'm going to apply. That negative. So that is going to give us the final thing, which is h of x. That is going to give us the final graph. And what is that negative going to do to the graph? We said it is going to affect the y values. So that negative on the outside affects the y values. It is going to reflect the graph over the x-axis. And that negative is basically going to multiply all of the y values times a -1. So that's what we're going to have next. So my new points are going to be -3, +8. Then -2, +1. Then -1, 0, that one stays the same. 0, -1. And 1, -8. So if you look at the new points, -3, 8, it's going to be up here. -2, 1. -1, 0. 0, -1. And then 1, -8. And that would be the graph of h of x that we were looking for. And that concludes this problem. Now just keep in mind that the only things we need to sketch is f of x and h of x. This one is extra. This is just, it probably helps us an aid to look at the transformations when you're describing. But again, it doesn't need to be graphed. So we only need f of x and h of x. So now we're going to describe how the graph of g and the graph of h are related to each other. So we're going to say that the graph of h of x is the graph of f of x. But first it was shifted 1 unit to the left, comma, and reflected about or across the x-axis. You can see that it was reflected downward. So that's what happened to the graph. So it was reflected over the x-axis to create this right here. The next topic. Now we're going to cover what is called the vertical stretching and vertical shrinking. So vertical stretching and shrinking happens when you have a constant c that is being multiplied to the function on the outside. So if you have a number c that is being multiplied to the function on the outside, that is going to create a vertical stretch or vertical shrink. And I'll show you in the graph how the stretch or shrink is going to look like once we get to that. Now, how do we know that it's going to create a stretch? If that number c that you're multiplying, it is greater than 1, then the graph is going to be stretched vertically. And the effect that it's going to have on the points is that it's going to multiply all of the y values by that number c. If that number c that is being multiplied is smaller than 1 but greater than 0, means a fraction, anything between 0 and 1, then the graph is going to be shrunk vertically, and it's also going to multiply the y values by that number c. Now, vertical stretch is basically telling you that it's going to make the y values bigger, and the vertical shrink is telling you that it's going to make the y values smaller. Okay, that's basically what's going to happen. Let's go ahead and take a look to the first function here. So we're going to discuss this one. Use transformations of f of x equals x to the second power to graph the following function. G of x equals negative 2 parentheses x plus 2 squared minus 4. So we need to begin again by creating a table for the function f of x. And the function is x squared. So we're going to use the values again, negative 2, negative 1, 0, 1, and 2. So what we need to do is we're going to square them each. So negative 2 squared is going to give us a 4. Negative 1 squared, it's going to give us a 1. Then 0 squared, it's going to give us a 0. Then 1 squared, it's going to give us a 1. And 2 squared, it's going to give us a 4. So let's write the points down here for f of x. So the function f of x equals to x squared is going to have the points negative 2 comma 4, negative 1 comma 1, 0 comma 0, 1 comma 1, and 2 comma 4. So these are going to be the points. So negative 2 comma 4, it is up here. Negative 1 comma 1, 0 comma 0, 1 comma 1, and 2 comma 4. So that would be my function f of x. Remember, the f of x equals x squared creates the shape of a u. Now, when we're applying the transformations, on this one we need to be careful on the way that we do it. Now, we first need to do the horizontal shift. That should be the first transformation. So the horizontal shift is going to be the x plus 2. And what is that plus 2 going to do according to the definition? It is going to shift the graph to the left 2 units. And what effect does it have on the points? It is going to subtract the x values by 2. So you're going to do minus 2 to all of the x values right here. So negative 2 minus 2 is negative 4, comma 4. Negative 1 minus 2 is negative 3, comma 1. 0 minus 2 is negative 2, comma 0. 1 minus 2 is negative 1, comma 1. And 2 minus 2 is going to be 0, comma 4. Let's graph those points. So we have negative 4, comma, and positive 4. then negative 3 and 1, negative 2 and 0, negative 1 and 1, and 0, comma 4. So the only thing that happened, as you can compare the two graphs, is that the graph of this one was shifted to the left 2 units. From here to here, it was shifted to the left 2 units. Now, second transformation. Now, the only thing that matters here that I want you to keep in mind is that the first thing that needs to be done is the horizontal shift, and the last one, it has to be the vertical shift. So that -4 must be the last transformation. Okay, so we have 2 more that we need to apply. We have a 2 in the front, and we also have a negative. Okay, now it doesn't matter which one is done first. So let's say I'm going to do the 2 first. This is a new concept that I just showed you on the previous slide. That 2, it is being multiplied. When you're multiplying a number on the outside, that's what I told you, that's going to create a vertical stretch or vertical shrink. And if it is greater than 1, just like this number, it's going to stretch it vertically. Now, what happens on the vertical stretch? All of the y values right here will be multiplied by that constant 2. So all of them will be multiplied by 2. So that's going to give us this. Negative 4 comma 4 times 2 is going to be 8. Negative 3 comma 1 times 2 is going to be 2. The next one. Negative 2 comma 0 times 2 is still 0. Negative 1 comma 1 times 2 is going to be 2. And 0 comma 4 times 2 is going to be 8. So negative 4 and positive 8, that's the first point. Then negative 3 and positive 2. Negative 2 and 0, negative 1 and positive 2, and 0 and positive 8. And this is what basically a vertical stretch looks like. It makes the graph basically become a little bit skinnier because the y values get larger. For every one of these points that we have here originally, the y values became larger. So basically it makes the graph look a little bit skinnier or narrower. That's what the vertical stretch causes. Now, the next transformation, now we're going to apply the negative. Okay? That negative in front of the 2. What that negative is going to do, it is going to reflect the graph over the x-axis. And that negative in the front on the outside is going to multiply the y values by a -1. That was the definition. So we're going to multiply all of the y values by a -1. Now, I'm going to tell you something that you could have done also, and that's completely okay as long as you can describe the transformation separately. Because right here, it stretched it vertically, and right here is going to reflect it downward onto the x-axis. Now, you see that I multiplied the y values times 2, and then the y values times a -1. It would have been the same thing if I would have multiplied the y values by the -2. But we can put them both in one transformation, but when you describe it, you need to describe each one separately. Okay, so give it a second. So the transformations for this one is going to be -4 comma -8. Because it just changes the sign, so it will probably multiply by a negative. -3 comma -2, -2 comma 0, -1 comma -2, and 0 comma -8. So all the y's are multiplied by a negative, which means all of the y's changes the sign. So from here, at this point, if I would have multiplied these times not 2 but -2, I was going to get these values. So -4 comma -8, -3 comma -2, -2 and 0, -1 comma -2, and the last one is 0 comma -8. And that's what we say, which is the graph was reflected downward over the x-axis. So from here to here, it was reflected downward over the x-axis. Okay. Last but not least, we are going to apply the -4. That would be my last transformation here to apply. So this is going to create already the function g of x. This will be the end. Okay, and the end would be this: -2 parentheses x plus 2 squared, which is what we did already up to here, but now we're going to finish it with the -4. That -4 is going to subtract the y values by 4, and it's going to bring the graph 4 units down. So that's why it subtracts 4 on the y values. So let's see what that is going to look like now. -4 comma -12, -3 comma -6, -2 comma -4, -1 comma -6, and 0 comma -12. And that's going to finish this. So -4, -12. Let's say it is -12 is here. -3 comma -6 is right here. -2 comma -4 is right here. -1 comma -6, and 0 -12 we're going to say is out here. And this is going to be my final graph for this function. So this is the graph of g of x. We can always use a graphing utility, graphing calculator, to put this graph and see what it basically looks like. But I'm going to do it separately, of course, to be able to describe the transformations at the end. So when we describe them, now on this one there's 4 descriptions we have to make, so be careful in the order. So we're going to say that the graph of g of x is the graph of f of x, but first of all it was shifted 2 units to the left, comma, then vertically stretched. Remember that too, what it cost? It stretched it vertically. So vertically stretched, and this is how you finish the sentence, by a factor of 2. So that was a factor of by which it was vertically stretched. So that's how you finish that sentence. Vertically stretched by a factor of 2. Then it was reflected over or across or about the x-axis. And finally it was shifted 4 units downward. And this is the complete description of how the graph of G is related to the graph of F. Before we go into the last question, so we have one more that we're going to do, then we're going to get to the last one. So we are going to do this question here. Like I said, there are some questions that ask you to describe, there are some that don't. So this is one that asks you to describe. So it says, describe how the graph of G is related to F, and then graph the function. So we're gonna first I'm gonna graph it, and then we're gonna write the description. Or you know what? I want you to write it to see if you know how basically, without looking at the graph, we can understand what the actual transformations will be. So if we were to transform this, what would be the best transformation? The first transformation would be the 1/3. Because the -3, that -3 is a vertical shift, and vertical shift should always be the last one. So I need to do this 1/3 and then the -3. So that 1/3 is going to make it's multiplying, so it's going to make the graph shrink or stretch, which in this case, since it is less than 1, it is going to make it shrink vertically. So it's going to create a vertical shrink, and then it's going to shift it 3 units down. So we can already describe it, and then we're going to look at the graph. So we're going to say that the graph of g of x is the graph of f of x, but we're going to say the shrunk vertically by a factor of 1/3 1/3 and shifted 3 units down or downward. Okay, that's what actually it's going to happen if we graph this function. It's going to shrink vertically by that factor of 1/3, and then that -3 tells you that it's going to be shifted 3 units downward. So let's go ahead and graph the transformations. So we're going to start with the function f of x as usual. F of x equals to x to the 3rd power. So we're going to use the values again, -2, -1, 0, 1, and +2. And then we're going to use the function -2 to the 3rd power is -8. -1 to the 3rd power is -1. 0 to the 3rd power is 0. 1 to the 3rd power is 1. And 2 to the 3rd power, it's going to be 8. So let's go ahead and put the points here. So for the function f of x equals x cubed, we got the following points: -2, -8, -1, -1, 0, 0, then 1, 1, and 2, 8. So let's graph this. -2, -8 is right here. -1, -1, then 0, 0, then 1, 1, and then 2 and +8 up here. Keep in mind the graph of x cubed looks like an S-shaped. This is what we would see on the graph. Now we're gonna continue with the next thing. So this is f of x. So we already mentioned that the first transformation that must be applied is the shrink in this problem. So we're going to start with the 1/3 x cubed. What is that 1/3 is going to do? It's going to shrink it vertically, and basically what it does, it multiplies all of the y values times 1/3. So once again, it multiplies all of the y values times that 1/3. So that multiply times 1/3 is the same thing as multiplying times 1 and then dividing by 3. So -8 times 1 is -8, but -8 divided by 3 it's going to be -2.6 or -2.7. Just to estimate at best, -2.7. The next one is going to be -1 comma, then -1 times 1 is -1/3 is -0.3. The next one, 0 comma, 0 times 1/3 it's going to be 0. 1 comma, 1 times 1/3 is going to be 0.3. And then the last one is 2 comma, 8 times 1/3 it's going to be 8/3, which is 2.7. So that creates my second transformation. So we got -2, -2.7, which is going to be somewhere in here. Now the next one is -1, -0.3, which is going to be somewhere in here. The next one is 0, 0. The next one is 1 and 0.3, which is somewhere in here. The next one is 2 and 2.7, which is going to be somewhere in here. And this is what a vertical shrink looks like. Vertical shrink or vertical compression, we call it either way. And it keeps on going this way, it keeps on going this way. Now, let's do the last one right here, which is going to be the -3. Yeah, the -3. That is going to create a vertical shift. So that is going to give us the end, which is going to be g of x. g of x equals to 1/3 x cubed minus 3. So what is that minus 3 is going to have as an effect? It is going to bring the graph 3 units down, which means that all of the y values are going to be subtracted by 3. So that's what's going to happen to these. So negative 2 comma negative 2.7 minus 3 is negative 5.7. Now negative 1 comma negative 0.3 minus 3 is negative 3.3. 0 comma 0 minus 3 is going to be negative 3. Now 1 comma 0.3 minus 3 is negative 2.7, and 2 comma 2.7 minus 3 is negative 0.3. And this will be my final points. So we are going to have negative 2, negative 5.7, which is going to be somewhere in here, negative 1, negative 3.3, which is somewhere in here, then 0, negative 3, 1, negative 2.7, somewhere in here, and the last one is 2 and negative 0.3, which is somewhere in here. And that is going to create the graph of g of x. And that completes this function right here. And we already described how the graphs are related. First, the graph was shrunk vertically by a factor of 1/3, and then the graph was shifted 3 units down to create this. Alright, so we got one more type of transformation that must be covered, and that will be the last one. So the next and last is going to be called a horizontal stretching and shrinking. This one tells us, let f be a function and c be a positive real number. Now, in this case, we're going to have a number c that is going to be multiplied, but it's going to be multiplied times x, times the x. So that c is going to be multiplied inside of the square root, inside of the parentheses, or whatever it is that the function looks like, inside of the absolute value. So that's where that number c is going to be located. It's going to be multiplied inside. So what that function, what that number c inside is going to do, is going to stretch or shrink the graph horizontally. So when that number c that it's inside is bigger than 1, then that is going to create a horizontal shrink, and you're going to do the opposite operation. You are going to divide the x coordinates by that number c. Now, when you are multiplying a number c in front of the x, but that number c is between 0 and 1, which is a fraction, then that number is going to cause the graph to horizontally stretch. And to get the values of the new values with the points, you're going to divide all of the x values by that number c. So that's what it creates. So if the number in front of the x is bigger than 1, then it creates a horizontal shrink, and you get it by dividing the x values by that number c. If that number in front of the x is between 0 and 1, then that's going to create a horizontal stretch, and you obtain it by dividing all of the x values by that number c. So let's work on the last transformation, and this is going to be my last question here. We're going to use the graph of f of x shown below to graph the function g of x equals f of 2x. Use the graph of f of x equals y equals f of x below to sketch the graph of g of x. Now, first thing that we're going to do, of course, is that we're going to label the points for the function f of x, which in this case we got negative 8, 0. Then we got negative 4, negative 4. Then we got 0, 0. Then we got 2 more, which in this case is going to be 4, 4, and the last one is 8, 0. So you see that there's only one transformation to apply, and the only transformation is g of x equals f of 2x. So you see that we have a 2 in front of the x, so that's going to create a horizontal shrink. That's what the 2 is going to do, and we obtain that horizontal shrink by dividing all of the x values by that number that is in front of the x. So I'm going to divide all the x's right here by that number 2. So that's going to give us -4, comma 0, -2, comma -4, 0, comma 0, 2, comma 4, and 8, comma 0. Okay, so it would be -4, 0 would be right here, -2, comma -4 is right here, 0 and 0, then 2, comma 4, and the last one is going to be, oh, that one was a 4 at the end, 4, comma, and 0. That would be the last one. So the graph was shrunk horizontally by a factor of 2. That's how we're going to explain it right here. How we obtain the graph of g, we're going to say that the graph of g of x is the graph of f of x, but horizontally shrunk horizontally by a factor of 2. And that would basically be all what we need to cover in this section. So this is the end of transformations of functions, section 2.5.